So right now we try to introduce the work, potential energy, and the kinetic energy. The first one we have to define the work. The work is done when the force is applied to the object, and the object moves in the same direction of the force. So the key word, the work is counted by the object moving in the same direction. So if we want to count by such kind of the value, we must use the inner product as the math tool. So the work actually as the inner product with the force and displacement. By the mass form, that one is the magnitude of the force and the magnitude of the displacement. The theta is the angle between the two of the vector. So if the force and the displacement is perpendicular, the work is 0. If it's parallel, they just simple to multiply with their magnitudes. So finally we got the work himself is a scalar. The reason is that one is the inner product of the two vectors. Then this one, we can write it by the more general case. The general case is that our path can be verified in the arbitrary path. So if we consider about this one, we can cut the path by the small piece. Then each of the small piece is the force inner product with the displacement. Then we just try to integrate all of the small piece. Or we said it's the sum of all of the small piece, small of the work. So the total work is the integration of the work done by the force with the path. Actually, it's along the path. So this one is a general form of the work. Then we just use one of the example to expand this formula. So right now we have the force. The force is the constant force. This one is a constant force and always point to the positive x-axis. And we have the object moving along the path, and the path is moving with the time. So at the beginning, t equal to 0, the position is 0, 0. And when moving, for example, the t equal to 2, the position is 2 and 2. So the path of the object is like this one. So current, we have the continue and constant force. And change path, change position, so we have the path. So the work, we can write it with the integration with the force inner product with displacement. And we can try to calculate the work done from the t equal to 0 to t equal to tn. Maybe t final is also possible. So this one is just the symbol. So when we try to integrate this value, we found this one, displacement, is not a function of the t. So we try to change the ds to the function of the t. Actually, the most simple way we know the displacement is the velocity times multiplied with the t. So we can rewrite the displacement with the velocity times t. And the velocity itself actually is the relative of the position vector, the first derivative. So we can write it down that the relative result is 2t over 2 and j. So the velocity directions always change in the different position along the path. But it doesn't matter, we just try to integrate with the force. Then we can get the final result is the t squared is t squared. So with the different time, the work done by the object is a variable, then the total work is Tn squared. This one is one of the example. So finally, we back to the final result. The work along the path is integration from the point 1 to the final point, and with the force and displacement. So right now we will go to the potential energy part. What is the potential energy? By definition, the potential energy is the energy stored in the object due to its position. So this one is dependent on its position. So most general case is the gravitational potential energy. So let us use the gravitational energy to expand what is the potential energy. So if we have the object original is at the 0 point. Then we just use the force to lift up the object from the 0 to the edge. The force himself must against the gravity. So the force is the mass of the object and against the gravity constant. Then force is the up positive y-axis. And the distance is the h and the positive y-axis. They are in the same direction. So the work integrated from the 0 to the edge actually is the inner product of the force and the displacement. But we know this one is the same direction, so it's very easy to just multiply the magnitude. So the force actually is mg and the displacement is h. So final result is mgh. So we can apply the force to lift the object to the high edge. The work is stored in the position h. When you release from the edge, you should release the same amount of the work or the energy out if the storage energy is function that depends on the position. Then the position at high is u of h, and the position energy at 0 we write down by the u of 0. The release energy is minus mgh. It's released. The minus sign means release. So the initial potential energy subtract the final position energy. We just write it by the change of the position energy is minus side. So delta U should be the released energy and minus side. So U of h should be greater than U of 0. And the change or the difference is mgh. So we can choose the u0 is 0 and uh is mgh. Or uh is 0, then u0 is minus mgh. They give us the same result. So then we try to expand the object released from a certain height. So let's try to release from the rest and from the high edge. Then after we release this one, The height actually is the half of the g times the t squared. Then the height himself is the half multiplied with the velocity and the g. This one actually is the v squared over the g. So we got this result. Then we can got the gh is the half of the v squared. Then we got the mgh is the half multiplied with the mv squared. That one is means about the radius position energy. Radius position energy. It's transferred to the object and gain some velocity. So we defined this value as kinetic energy. Kinetic energy. So we got the kinetic energy. That one, the kinetic energy, EK, is the half of the mv squared and equal to mgh. Then we got the delta U, the change of the potential energy, is minus mgh. Please remember this one is the release energy. And the release energy will become the kinetic energy. So finally we found the change of potential energy and the change of the kinetic energy will be the zero. The zero means this one is independent of the time. Or we said the total change of the potential energy and the kinetic energy is zero. Or we said is the conservation with the time. So this formula, it means the conservation of the mechanical energy. So how to get the mass form of the kinetic energy? If the force acts on the object with the mass m, so we can start from the Newton law. F equal to m multiplied with a. Sorry, we must adding the error in here. The work done on the object for the some distance is the force inner product with the displacement. So then we can find that the work himself actually is the force inner product with the displacement. We write it and move the mass out. Then we can get this one is acceleration with the displacement. And the acceleration actually is the relative with the velocity. So we just write it down by the dv, and the dv dt actually is velocity. So finally we got the mass times the integration of the velocity dv. Then we integrate this formula. Then we got the half and the v squared. Then one will give us the half times the mass times the velocity squared. And this one is a kinetic energy. So that's the reason the kinetic energy is a half multiplied with the mass times the v squared. Then we can also have an example of elastic potential energy. So if we have the spring, this one is a natural position. The natural position is mean about the length of the spring. That one, the spring don't have any external force or internal force. Then we have the force to put out the spring. Then we will make the displacement of the spring or external distance of the spring. Then we can find the relation between the displacement and the external force is F equal to Kx. the K is the sum of constant, or we could say this one is a coefficient between the displacement and the external force. So we try to calculate the work. The work himself is the F multiplied, it should not be multiplied, in the product with the displacement. So we just let the K out. Finally, we have the X, integrate with the X. So then we can get the half and kx squared. So this one is the potential energy. Of the spring. So finally, we already introduced what is the work, what is the potential energy, and what is the kinetic energy. Let us summarize the result in here. If we have the force and apply to the sum of the object and moving with the sum displacement, the work is the integration from the initial point to final point and the force in the product with the displacement. The potential energy himself actually is the storage of the energy that depends on the position of the object. So actually that one is depend on the work. And the kinetic energy is the half and multiply with the mass and the velocity square, EK. Then if we have changed the kinetic energy, then you will be save or release the energy in the potential energy. So we can get the conservation of the energy. That one is the change of the potential energy, and the change of the kinetic energy is 0. This one is conservation.